All right, let's jump right in. We're going to pull back the curtain on one of the most powerful and maybe misunderstood ideas in all of math, the function. Seriously, it's like the hidden language that describes how the world actually works, and by the end of this, you're going to be fluent.
So let me ask you a question. What could possibly connect the path of a rocket soaring into the sky with the way your bank account grows over time? It seems random, right? Well, the answer is a single, really elegant concept that once you see it, you'll start spotting it absolutely everywhere.
To really get this, let's just forget about all the complicated math stuff for a second. Instead, I want you to picture something much, much simpler, the perfect vending machine. Because at its heart, a function is just a rule. That's it. A totally predictable rule that guarantees when you put something in, you get one specific thing out. Every single time. No surprises, no guessing games.
Think about it like this. Your choice, pressing button B4, that's your input. The machine's programming, the gears turning inside, that's the rule that connects your input to a specific snack. And the output? Well, that's the delicious bag of pretzels you get. The key here, the magic, is the consistency. You press B4, you get pretzels. Not a soda, not chips. That absolute reliability is the very soul of a function.
And this brings us to what I like to call the golden rule of functions. One input can only ever lead to one unique output. This isn't just some random math rule, it's what makes them so incredibly useful. I mean, you wouldn't trust your GPS if you typed in an address and it gave you two different routes at the same time, would you? Of course not. You need that predictability.
Okay, so the vending machine idea makes sense. But how does this translate into the world of graphs and charts? How can you just glance at a graph and know instantly if it's following our golden rule?
Well, there's this super simple trick called the vertical line test. It's awesome. Just imagine sliding a vertical line, like a ruler, all the way across the graph. If it only ever touches the curve at one single point at a time, then congratulations, it passes the test. It's a function. See here? No matter where that line goes, it only hits our curve once.
But now, look at the circle. When we slide our vertical line across, it hits the curve in two places at once. What does that mean? It means one input, that one spot on the horizontal axis, is trying to create two different outputs. And that breaks our golden rule. So a simple circle? Nope, not a function.
So now that we've got the core idea down, let's learn how to speak the language. Functions have their own special notation, their own vocabulary, that actually makes everything way clearer once you get the hang of it.
You've probably seen equations like y equals 2x plus 3 a million times. Well, function notation is just a cool upgrade. Instead of y, we write f of x, and you say it out loud as f of x. The f is just a name we give the function. We could call it g of x or h of x, whatever. The x in the parentheses just tells us what our input variable is. And listen, this is super important. F of x does not mean f times x. It's just a label for the final output.
What's great about this is that it makes the cause and effect relationship crystal clear. The independent variable, our x, that's the cause. It's the thing you control, the button you press. The dependent variable, our f of x, that's the effect. Its value totally depends on what you chose for x. So when you hear a phrase like evaluate a function, don't let it scare you. It's just a fancy way of saying plug in a number and see what pops out. If our rule is f of x equals 2x plus 5, and we want to find f of 3, we just replace every single x we see with the number 3. So 2 times 3 is 6, add 5, and you get 11. That's it. Simple. Okay, theory time is over. Let's get to the fun part. Where do these things actually show up in the real world? Because I promise you, once you start looking, you'll see they are everywhere.
Ever convert Fahrenheit to Celsius? Yep, that's a function. You input a Fahrenheit temperature, the rule does its thing, and it outputs Celsius. Calculating the final cost of something with sales tax? That's a function too. Heck, the code that runs your phone, your computer, it's all built out of little functions. You've been using them your whole life without even realizing it.
And it's not just everyday stuff. This whole input rule output model, it's the actual backbone of science and technology. In finance, your input is time, the rule is the compound interest formula, and the output is your account balance. In medicine, a doctor inputs a patient's weight into a dosage formula to get the exact amount of medicine needed. Functions turn information into prediction. Now, just like in the animal kingdom, functions can be sorted into different families based on how they behave. We're going to meet the 3 most common ones, because recognizing them is the key to understanding the different ways that things can change. So here's a quick look at the big 3.
You've got linear functions, which make straight lines and represent steady additive change. Then you have quadratic functions, which make those U-shaped parabolas and show accelerating change. And finally, exponential functions, which create these J-shaped curves that represent explosive, multiplicative change. Each one tells a totally different story about growth.
First up, we've got the straight shooter, the linear function. This is your reliable workhorse. Its change is steady, constant, and predictable. For every step you take forward, you go up by the exact same amount. Think of a car with the cruise control locked in. That's linear change.
Next, we've got the curveball, the quadratic function. This one models things that speed up or slow down over time. The classic example is throwing a ball into the air. It goes up, slows down, hangs for a second, and then accelerates back to Earth. That perfect arc is a parabola, and it's quadratic motion in action.
And finally, we have the rocket ship, the exponential function. And this is where things get wild. This isn't about adding, it's about multiplying. It's about doubling and doubling again. This is the engine behind things like compound interest or how a video goes viral. It starts slow, and then it just explodes.
So, why should you care about these different families? Because truly understanding the massive difference in how they grow, well, it gives you a completely new way to see and interpret the world around you.
To really see what I mean, let's have them race each other. So after just 15 steps, our linear function is at a respectable 30. The quadratic is way ahead at 225. Pretty impressive. But look at the exponential function. It's at almost 33,000. It didn't just win the race, it completely broke the scale. That is the jaw-dropping power of multiplicative growth.
And that right there, that's the whole point. Understanding functions isn't just about passing a math test. It's about getting a new lens to view the world through. It really is a superpower that lets you see the hidden patterns and the invisible rules that drive change all around us.
So, I'll leave you with this challenge. Now that you speak the language, what relationships, what rules, what hidden functions are you going to spot out there in the world today?